Welcome to this solution walkthrough. In this video, we'll explore problem number 72, edit distance. This is a classic dynamic programming challenge that focuses on calculating the minimum number of operations required to transform one string into another. These operations include insertions, deletions, and substitutions. Let's dive in and break this problem down step by step. The edit distance problem is a foundational problem in dynamic programming and focuses on determining the minimum number of operations needed to transform one string into another. These operations are limited to three types: inserting a character, deleting a character, or replacing one character with another. The goal is to calculate the minimum number of such operations required to convert the string word1 into word2. The input consists of two strings. Word1 is the initial string and word2 is the target string. The output is a single integer representing the minimum number of operations required to achieve the transformation from word1 to word2. To better understand the problem, let's explore some examples. In the first example, we have word1 as horse and word2 as rose. The minimum number of operations required is 3. First, replace h with r to get rorse. Next, remove r to form rose, and finally, remove e to reach rose. This sequence of three operations transforms horse into rose. For the second example, given word1 as intention and word2 as execution, we will see that the transformation requires more steps. In the second example, transforming intention to execution requires 5 operations. First, replace I with e to form endion. Then, replace the first n with x, giving us extion. Next, insert e to make exection. After that, replace c with u to form execution, and finally, insert n to complete the transformation into execution. In the third example, transforming abc to yabd requires just 2 operations. First, insert y at the beginning to get yabd, and then replace c with d to arrive at yabd. These examples illustrate the kinds of operations and their sequences that minimize the transformation cost. Now, considering the constraints, both word1 and word2 can have lengths between 0 and 500, and they consist only of lowercase English letters. If one of the strings is empty, the minimum number of operations required is simply the length of the non-empty string, as we would need to either insert or delete all its characters. This problem also exhibits an important property called optimal substructure, which means that the solution to the overall problem can be built from solutions to *its subproblems. This property makes it a perfect candidate for a dynamic programming approach. The time complexity of the optimal solution is O(m*(n), where m and n are the lengths of word1 and word2, respectively. Depending on the implementation, the space complexity can range from O(m*(n) for a full DP table to O(m*(n) for a space-optimized variant. The edit distance problem is a fundamental dynamic programming challenge, where the goal is to find the minimum number of operations needed to transform one string into another. These operations include inserting a character, deleting a character, or substituting one character for another. To solve this, we can consider multiple approaches. First, the brute force approach involves exploring all possible sequences of operations. For each character in the two strings, we compare them. If they match, we move to the next pair. If they don't, we recursively try the 3 operations insert, delete, or replace and choose the one with the minimum cost. However, while this approach is intuitive, it's computationally expensive, with exponential time complexity of O(3)m+n due to the branching at each step. This inefficiency arises from redundant calculations and overlapping subproblems. To address these drawbacks, we turn to an optimized approach using dynamic programming. Here, we construct a 2D table, where each cell represents the minimum edit distance for converting a prefix of one string to a prefix of another. If the characters being compared are the same, no operation is needed, and we simply inherit the value from the diagonal cell. If they differ, we compute the minimum cost by considering replace, insert, or delete operations, and adding 1 to the corresponding value. In addition to replace and insert, the delete operation is also considered in the dynamic programming approach. For deletion, we look at the value from the cell representing the previous prefix of the first string and add 1. By evaluating these 3 possibilities, replace, insert, and delete, we determine the minimum edit distance for each cell. This approach has a time complexity of O(m*(n), where m and n are the lengths of the two strings, and a space complexity of O, m asterisk n, to store the DP table. To further optimize space usage, we can replace the full 2D table with a rolling array that only keeps the current and previous rows, reducing space complexity to O, n. Another potential approach is recursion with memoization, which builds on the brute force method. Here, instead of recalculating the same sub-problems repeatedly, we store intermediate results in a memoization table. This improves time complexity to O, m asterisk n, by eliminating redundant calculations. However, recursion with memoization has its own limitation, managing recursive depth. With very large inputs, the recursive stack can become too deep, potentially leading to stack overflow. These considerations make dynamic programming a more robust solution. The dynamic programming approach, especially with space optimization using a rolling array, was ultimately chosen as the best strategy due to its efficiency, clarity, and scalability. By breaking the problem into smaller subproblems and solving each just once, we achieve a time complexity of O, m asterisk n. The rolling array reduces memory usage significantly, making this approach well suited for large inputs. Brute force was ruled out because its exponential time complexity makes it infeasible for even moderately sized strings. Recursive memoization, while an improvement, still involves recursion overhead and risks stack overflow for large inputs. Dynamic programming strikes the right balance, offering both time efficiency and space optimization. One trade-off to note is that while rolling arrays save memory, they can make debugging slightly more challenging compared to working with a full DP table. However, this trade-off is worthwhile as the solution scales effectively for strings up to the problem constraint of length 10 cubed. The key insight, or the aha moment, was recognizing that the problem could be divided into overlapping subproblems and solved iteratively using a DP table. This insight not only eliminates the need for recursion but also paves the way for space optimization by focusing on just the current and previous rows of the table. The edit distance problem involves transforming one string, word1, into another string, word2, using the minimum number of operations. These operations include inserting a character into word1, deleting a character from word1, or substituting one character in word1 with another. The goal is to compute the minimum number of these operations required to make the transformation. To solve this efficiently, we use dynamic programming. We define our state as dp, I, j, which represents the minimum edit distance between the first I characters of word1 and the first j characters of word2. Now, for the base cases, if word1 is empty, meaning I equals 0, then the edit distance is simply the length of word2, as we would need to insert all j characters of word2 into word1. This is represented as dp, 0, j, equals j for all j. If word2 is empty, meaning j equals 0, the edit distance would be the length of word1, as we would need to delete all I characters of word1. This is represented as dp, I, 0, equals I for all I. Now, for the recursive relation, we consider each pair of indices I and j, looking at the last characters of the substrings. If the characters are the same, no operation is needed, so dp, I, j, equals dp, I1, j1. However, if the characters differ, we must consider all three possible operations: insertion, deletion, and substitution. For insertion, we add the jth character of word2 to word1, making the cost dp, I, j1, plus 1. For deletion, we remove the ith character from word1, making the cost dp, I1, j, plus 1. For substitution, we replace the ith character of word1 with the jth character of word2, making the cost dp, I1, j1, plus 1. Combining these cases, we take the minimum of the three values, dp, I, j equals min, dp, I1, j plus 1, dp, I, j1, plus 1, dp, I1, j1, plus cost. Here, the cost is 0 if the characters match, and 1 otherwise. Once we define the recurrence, we calculate the values iteratively. For each I from 1 to the length of word1 and each j from 1 to the length of word2, we compute dp, I, j, using the relation we just developed. At the end of this process, the edit distance between word1 and word2 will be stored in dp, len, word1, len, word2. This is the final result. The key insights behind this algorithm are rooted in dynamic programming principles. First, the problem exhibits optimal substructure, meaning it can be broken into smaller overlapping subproblems. For instance, transforming smaller substrings of word 1 and word 2 provides the foundation for solving the larger problem. These overlapping subproblems make dynamic programming an efficient choice, as we avoid redundant calculations by storing intermediate results in a 2D DP table. Edge cases, such as when one or both strings are empty, are also naturally handled by the base cases. If both strings are empty, the edit distance is 0. If only one string is empty, the edit distance equals the length of the other string. In terms of data structures, we use a DP table. This is a 2D array of dimensions, len, word 1, plus 1, x, len, word 2, plus 1. The rows correspond to prefixes of word 1, and the columns correspond to prefixes of word 2. Each cell in the table stores the minimum edit distance for the corresponding pair of substrings. This table is essential for efficiently storing intermediate results and ensuring that we don't recompute the same values multiple times. Now, analyzing the algorithm's complexity, the time complexity is O(m*n), where m is the length of word 1 and n is the length of word 2. This is because we compute dp, I, j, for all pairs of I and j. The space complexity is also O(m*n) due to the 2D DP table. However, this can be optimized to O(min)n by using a rolling array, as we only need the current and previous rows at any given time. To better understand the algorithm, let's walk through an example. Consider word 1 equals horse and word 2 equals rose. First, we initialize the DP table with the base cases. Then, we fill the table row by row, comparing characters of word 1 and word 2, and calculating the minimum operations using the recurrence relation. For this example, the final DP table would look like this: rows labeled as H, O, R, S, E and columns labeled as R, O, S. The numbers in the table represent the minimum edit distances for each pair of substrings. After filling the table, we find the result in the bottom right corner of the DP table. For word 1 equals horse and word 2 equals rose, the value in DP, 5, 3, is 3. This means the minimum edit distance between the two strings is 3. Therefore, it would take 3 operations to transform word 1 into word 2. In this case, the operations could be deleting H, substituting E with O, and deleting the final E. This concludes the explanation of the edit distance algorithm, highlighting the use of dynamic programming to efficiently calculate the minimum number of operations required to transform one string into another. Here, we define a Python class called solution and its method minDistance, which calculates the minimum edit distance between two strings, word 1 and word 2. First, we determine the lengths of the input strings and store them in m and n. Next, we create a 2D dynamic programming table, DP, with dimensions m+1 by n+1. This table will help us store the results of subproblems, avoiding redundant calculations. Initially, we set up the first row and column of the table to handle base cases. Specifically, the first row represents the cost of inserting characters into word 1 to match word 2, while the first column corresponds to the cost of deleting characters from word 1. Once the base cases are initialized, we move on to filling the rest of the table. For each cell in the table, we check if the current characters of the two strings match. If they do, no operation is needed, and we carry over the value from the diagonal cell. Otherwise, we calculate the cost of the 3 possible operations, insertion, deletion, and substitution, and take the minimum of these, adding 1 to account for the current operation. This process systematically builds the solution for the entire problem, one subproblem at a time. Finally, the answer to the problem is found in the bottom right cell of the dynamic programming table, DP, m(n). This value represents the minimum number of operations required to transform word 1 into word 2. By returning this value, we complete our implementation of the minDistance function. This approach ensures that we compute the result efficiently, using dynamic programming to break the problem into manageable subproblems while avoiding redundant calculations. Here, we start by defining our method minDistance, which takes two strings, word 1 and word 2, as input. These represent the two words for which we want to calculate the minimum edit distance. First, we obtain the lengths of these words and store them in m and n, respectively. Next, we create a 2D array DP with dimensions m+1 x, n+1. This table will help us store the minimum operations required to convert substrings of word 1 into substrings of word 2. Now, we initialize the first row and column of the DP table. The first row represents the cost of transforming an empty word1 into increasing prefixes of word2 using only insertions. Similarly, the first column reflects the cost of transforming increasing prefixes of word1 into an empty word2 using deletions. Once the initialization is complete, we move on to filling the rest of the table using nested loops. For every cell DP, I, J, we compare the characters word1, I1, and word2, J1. If they match, no operation is required, and the value is carried over from DP, I1, J1. On the other hand, if the characters differ, we calculate the minimum cost of three possible operations: deletion, represented by DP, I1, J, insertion, represented by DP, I, J1, and substitution, represented by DP, I1, J1. We add 1 to the minimum of these three values and update DP, I, J. This way, the table is filled row by row, with each cell representing the minimum edit distance for the respective substrings. Finally, the bottom right cell of the table, DP, MN, contains the answer to the problem, the minimum number of operations needed to convert word1 into word2. This approach ensures that we systematically evaluate all possibilities while leveraging previously computed results to optimize the solution using dynamic programming. In this problem, we're tasked with finding the minimum number of operations required to convert one string, word1, into another string, word2. The allowed operations are inserting a character, deleting a character, or replacing a character. To solve this, we use a dynamic programming approach. For example, if word1 is horse and word2 is rose, we first start by initializing some variables. Here, the lengths of the strings are m equals 5 and n equals 3. Next, we create a dynamic programming table DP of size, m+1 and fix, n+1, where each cell will represent the minimum edit distance between the corresponding prefixes of the two strings. Initially, this table is filled with zeros, as shown here. Now, we initialize the base cases for the DP table. The first row represents converting an empty word1 into progressively longer prefixes of word2, so DP, 0, J, is set to J, corresponding to inserting characters into word1. Similarly, the first column represents converting progressively longer prefixes of word1 into an empty word2, so DP, I, 0, is set to I, corresponding to deleting characters from word1. Once these base cases are set up, we fill in the rest of the table. For each cell DP, I, J, if the characters in word1 and word2 at positions I1 and J1 match, the value is carried over from DP, I1, J1. Otherwise, we take the minimum of three possible operations, delete, insert, or replace, and add 1 to account for the current operation. As we iteratively update the table, we can see how these values are calculated step by step. When we finish filling out the DP table, the value in the bottom right corner, DP, 5, 3, gives us the minimum edit distance between horse and rose, which is 3. To further illustrate this approach, let's consider another example where word1 is intention and word2 is execution. Here, both strings have a length of 9. We again initialize a DP table of size, m+1 fx, n+1, and set up the base cases as before. Then, we iteratively compute the values for each cell based on the recurrence relation. The table updates progressively, and each cell represents the minimum cost to convert the corresponding prefixes of the two strings. This process ensures that we account for all possible operations at each step. At the end of the computation for the second example, the value in DP, 9, 9, is 5, which represents the minimum edit distance between intention and execution. From this, we can draw some key takeaways. First, the DP table allows us to track the minimum edit distance at each substring level systematically. Second, the base cases ensure that conversions involving empty strings are handled properly. Third, the recurrence relation guarantees that the minimum cost is calculated by considering all three possible operations: insert, delete, and substitute. Finally, the time complexity of this approach is O, m*n, and the space complexity is also O, m*n, making it efficient for this type of problem. The time complexity of the algorithm is determined by the two main steps: initializing the DP table and filling it. First, the initialization step involves setting up the first row and column of the table, which takes O, m+n, time. This is because the first column requires O, m iterations for each row, and the first row requires n iterations for each column. After initialization, we move to the main computation, where we fill the entire DP table. The table has dimensions m+1 by n+1, and we process each cell individually. For each cell, we compute the minimum of 3 values, representing the costs of insertion, deletion, and substitution. Since this computation takes constant time, or O1, and we perform it for every cell in the table, the total time for this step is m*n. Combining both steps, the table filling dominates, so the overall time complexity of the algorithm is m*n. The space complexity of the algorithm arises from the use of the DP table. This table is a 2D array with dimensions m+1 by n+1, where m is the length of the first word and n is the length of the second word. The space required to store this table is proportional to the product of its dimensions, which is m*n. Additionally, the algorithm uses a few auxiliary variables like loop counters and constants, but these require only O1 space and are negligible compared to the space for the DP table. Therefore, the overall space complexity of the algorithm is dominated by the DP table, making it m*n. When comparing this dynamic programming approach to a brute force solution, the efficiency becomes clear. A naive recursive solution explores all possible combinations of edit operations for both strings, resulting in an exponential time complexity of 3 m plus n. This happens because at every step, the algorithm considers 3 choices: insert, delete, or substitute, and the recursion depth depends on the total length of the 2 strings. In contrast, the dynamic programming approach drastically reduces the complexity to m*n by solving overlapping subproblems and storing their results in the DP table. This avoids redundant computations and makes the algorithm far more efficient. Furthermore, the time and space complexity of the DP approach remain m*n across best, average, and worst cases, as the algorithm always processes the entire DP table regardless of the input. There are no shortcuts or early exits based on specific scenarios. To mathematically verify the big O complexity, consider the nested loop structure of the algorithm. The outer loop runs m times, corresponding to the rows of the DP table, and for each iteration of the outer loop, the inner loop runs n times, corresponding to the columns. Inside the inner loop, operations like comparisons and minimum calculations are performed, each taking constant time O1. Multiplying these together, the total number of operations is m*n*O1, which simplifies to m*n. For space complexity, the dominant factor is the DP table itself, which has fixed dimensions of m+1 by n+1. This requires m*n memory, as the table size is directly proportional to the product of these dimensions. Thus, both the time and space complexity of the algorithm are rigorously proven to be m*n. When working on the edit distance problem, there are a few common mistakes that can cause incorrect results. First, not properly handling base cases is a frequent issue. Remember, the first row and column of the dynamic programming table must be initialized. These represent the cost of transforming an empty string into another string, which requires a series of insertions or deletions. Another common mistake involves misunderstanding the dynamic programming transition relation. For each cell, you need to account for 3 operations: an insertion, which corresponds to the value in DP, j1, plus 1, a deletion, which corresponds to DP, I1, j, plus 1, and a replacement, which involves the diagonal value DP, I1, j1, plus a cost. The cost here is 1 if the characters being compared are different, and 0 if they are the same. Off by 1 indexing errors are another pitfall, especially when accessing characters in the strings. Lastly, it's important to consider space optimization. For large inputs, a full 2D table can consume significant memory, and using only the current and previous rows can make your solution more efficient without sacrificing correctness. Edge cases are another critical area to watch out for. These include scenarios like empty strings, strings with only 1 character, or 2 identical strings. Properly testing your solution against these ensures it handles all possible inputs. When discussing this problem in an interview, focus on clearly explaining the recurrence relation. Show how each operation insert, delete, and replace contributes to the solution. Highlight the time and space complexities of your approach. The time complexity is O, m asterisk n, where m and n are the lengths of the two strings, and the space complexity is O, m asterisk n, for the full DP table. If you use the space-optimized version, the space complexity reduces to O, min, m, n. Be ready to discuss the trade-offs between these approaches. While the full DP table is easier to implement and debug, the space-optimized version is better suited for large inputs. Additionally, you might encounter variations of this problem, such as scenarios where only insertions and deletions are allowed, without replacements. The edit distance problem is closely related to several other dynamic programming problems. For example, LeetCode 1143 focuses on finding the longest common subsequence, while LeetCode 516 deals with the longest palindromic subsequence. Of course, the current problem, edit distance, fits into this family, and LeetCode 583 addresses a variation involving the delete operation for two strings. As for alternative approaches, one option is a purely recursive solution. This approach is intuitive because it breaks down the problem by directly considering all operations insert, delete, and replace. However, it comes with a major drawback. The time complexity is exponential, specifically O, 3 m plus n, due to repeated subproblems. This makes the recursive approach unsuitable for anything beyond very small inputs. A better approach is the bottom-up dynamic programming method, where we iteratively fill a 2D table based on the recurrence relation. While this is more efficient than recursion, the trade-off is its O, m asterisk n, space requirement, which can become a concern for very large strings. To address the space concerns of the bottom-up dynamic programming approach, we can use a space-optimized version. Instead of storing the entire 2D table, we only keep track of the current and previous rows. This reduces the space complexity to O, min, m, n, making it much more scalable for large inputs. The trade-off here is that implementing this version is slightly more complex, as you need to carefully manage the rolling rows to ensure correctness. However, this optimization is often necessary when working with constraints that involve large strings, and it demonstrates a deeper understanding of dynamic programming principles in both interviews and real-world scenarios. Great job! To recap, we tackled the edit distance problem using dynamic programming to calculate the minimum operations required to transform one string into another. We discussed the time and space complexities and highlighted the importance of dynamic programming in solving optimization problems. Keep practicing, and don't forget to like, subscribe, and stay tuned for more problem walkthroughs. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!